Okay, so now I want to derive the traffic equation, and in the next video we'll work on solving and analyzing some of these problems. So we're going to have the following. So u of xt is going to be the local density of cars. So it's a local density of cars, so the number of cars per mile, the number of cars per foot, whatever you want to have your units here. And then v of xt is equal to the local velocity of the cars. Okay, so u of xt is equal to the local density of the cars, and v of xt is equal to the local velocity of the cars. Now, what that means is that if I look at position x at time t, it means the cars that are going past me are going that speed. With this, we get the following equation. This is just a normal continuity equation. The partial derivative of u with respect to t plus the partial derivative with respect to x of v times u is equal to 0. We've seen this many times where u is a density and v is the velocity of whatever's the density of. So it could be wood chips flowing through the water. We saw v here was 1 plus x, and then an example after that, v was 1 plus x squared. What we want is, in real life, the velocity typically depends on the density of traffic. And so we want a function, we want v to actually be a function of u. And we wanted to satisfy a few properties. So this model is a model that was introduced by the author of the textbook, the official textbook of the course, Haberman, but also some other people, Lightfoot and Whitman. Sorry, I should have remembered what that is. Anyways, we wanted to satisfy several things. We want v of 0. So in other words, if the density is 0, I mean obviously if there's one car it's not going to be 0, but if it's close to 0, we want v of 0 to be equal to some maximum velocity, which I'm going to call v sub n. So if v, that looks like a square root. Sorry, unfortunately the v's, my v's and u's look alike. So v of 0 is going to be equal to some maximum velocity. So at 0 density, we're going to have some maximum velocity. Sort of on the flip side, we want to say that v of some maximum density is equal to 0. So if the cars are packed so tightly, no one's moving, we've got gridlock. So the velocity of this, theoretical maximum density is equal to 0. Okay, so we want v of 0 to be equal to vm, v of um to be equal to 0. If I kind of graph this on the uv axis, the easiest thing is to have a line. Here, this is v equals vm. Here, this is u is equal to u. There's other things we could take as well, like 1 minus x squared, or something like that. You'd have to get the constants right, but something like that would also work. There's other things. We could have something that looks like that, and so on and so forth. There's a number of different things that we could use here. But this is the simplest, and that's what we're going to go with. And so we've got v of u then is going to be equal to vm times times 1 minus u over um. So let's check that this does what we want it to do. If u is equal to 0, v of 0 is equal to vm. So check on that side. If u is equal to um, u over um is equal to 1, and 1 minus 1 is equal to 0. Now, oftentimes, what we want to do, these parameters, v sub m and u sub m, are going to depend on the road, the people driving, all of these sorts of things. And when we do the analysis, we don't always, yes, obviously, sometimes we want to take those into consideration, but if we're just doing a general qualitative analysis, we want to see what's going on. We want to sort of abstract away from those ideas, or abstract away from those things. Now, if we're actually doing traffic engineering, we would obviously need to know what those numbers were to be able to do things like time traffic lights and this sort of thing. Okay, but if we just want to do a qualitative analysis to get an idea qualitatively of what's going on and then put in the actual numbers later, we don't want the qualitative analysis to depend on these parameter values, unless, of course, I mean, sometimes it might actually depend on those. There might be things that change. But anyways, we don't want our general analysis to depend on those. So what we're going to do, instead of measuring density in terms of absolute density, we're going to measure density as a percentage of the maximum density. And similarly, instead of measuring velocity in terms of the actual velocity of the cars, we're going to measure the velocity in terms of the a percentage of the actual velocity. Or sorry, percentage of the maximum velocity. And so what this tells us then is v of u is just going to be equal to 1 minus u. And if the traffic density is 1, that doesn't mean 1 car per mile. The traffic density of 1 means we are at the maximum density. Similarly, if the velocity is 1, that doesn't mean we're moving at 1 unit. It means the velocity is equal to the maximum velocity, whatever those parameters are for the problem. Okay, so now let's come back over here. I'm just going to erase all of this stuff now. So v of u, the equation then is going to be the t derivative of u plus the x derivative of v of u times u is equal to 0. If I write this out a little bit further, v of u is 1 minus u, so this is u minus u squared equals 0. When we have it in this way, we call this conservative form or conservation form. And it's going to be important for the stuff that we do next week. It's going to be important to be able to write an equation in this way. And for the stuff that we're going to do today and next week, it's important to be able to expand this. So what I mean is the following. I can do the chain rule on this. We're going to have 1 minus 2u times the x derivative of u is equal to 0. Okay, so this here is the traffic equation. This models the flow of traffic under some assumptions. The same assumptions, I didn't mention them explicitly, but it's the same assumptions that we've always had. Cars are flowing down the road. They can't go into or off of the road. They're just flowing down the road. Now, obviously, when you flow down a road, if you've ever driven, you know that you can get off of the road and you can get on the road, because most of you are hopefully not on the road now, but have been on the road at some point. Therefore, if you're on the road, you can come off. So this model obviously has some limitations, but we're going to model the following situation. We're going to model situations where traffic light, today we're going to model the situation where a traffic light turns from red to green. Now, if I want to model what happens just close to the traffic light, when a traffic light turns from red to green, now this model makes a little more sense. Most cars are either going to go straight, or they're not going to come on, or they're not going to get off near the traffic light. They're just going to go through the intersection. Obviously, cars can turn. That's an important part. But we can say not a lot of cars are turning, and so this is a fairly suitable model. All right. This also can model other things. Once we look at this, you can see maybe how this model can work for highway traffic and stuff like that. And I'll say more about that next week. All right. So what we want to look at. So again, let me just put the equation here. The t derivative of u plus 1 minus 2u times the x derivative of u equals 0. This is the PDE that governs traffic flow. What I want to discuss now, what I want to set up now, and I'll solve in the next problem or the next video, is I want to set up a situation where a traffic light turns from red to green. So let's give a schematic here. So as typical, the horizontal axis will be the t-axis, and the vertical axis will be the x-axis. That's a lovely sound. That screeching sound is probably the one thing the microphone accurately picks up. For some reason, this whiteboard or this glass board just does not like black markers all the time, and I can't quite figure it out. Okay. So we imagine that at location x equals 0, we have a traffic light, and it's red, at time t equals 0, it's red. And we want to see what happens. We want to see what happens after that. So at time t equals 0, it's red. We want to see what happens after that. Okay, so what we're going to have then, if we look at x greater than 0, if you think about being stuck at a traffic light, there's no cars in front of you. So we're going to imagine the density of the cars up here is equal to 0. Okay, now obviously maybe there's people turning left this way or right that way, but let's just imagine the situation where that either doesn't happen or they get through the intersection, the light's red for everybody for a while, and so effectively the density in front of you is going to be equal to 0, and then we just extend that out forever. Essentially because a car half a mile in front of you is probably not going to affect what you do here at the traffic light when you go. Now on the other hand, if there's a traffic light, cars have all come to a stop, and we assume that the density is pretty much a maximum over here. So in our units, this just means 1, but it means a percentage of the maximum density. So almost bumper to bumper. I guess that's maybe not safe, but whatever. We have a maximum density over here. Okay, so at time t equals 0, we have a maximum density over here. We have a minimum density over here, and then we want to see what happens after that. So we'll write this over here as u of x0 is equal to 1. For x less than 0, it's equal to 0 for x greater than 0, and we want to see what happens. We want to basically solve this equation and see what happens after that. Now, the other thing I want to mention, u equals 1 less than infinity. Obviously, there's not an infinite number of cars, but again, if we just are looking at some subsection, then basically, for these cars up here, it doesn't matter really how many cars are behind them in terms of what they're going to do when they go forward. So these are just approximations that we make. Obviously, they're not literally true, but if you just want to kind of analyze the dynamics of what's happening locally, both in time and in space near the traffic light, these are both reasonable assumptions to make. Now in the next video, you're going to solve this equation. It's going to be very similar to what we saw before. Procedurally, it'll be very similar at least to what we saw before.